Hi everyone. Today we're going to be completing our notes on 4.4 Laws of Logarithms, or Properties of Logarithms. I want to start just by evaluating a bunch of logs and see if we can draw a pattern from some of these logs that we're evaluating. So go ahead and take out your calculator. We're going to start with log of 15. Now remember this log, there's no base written here, so we can assume that it's the common log, or log base 10. Once you have your calculator out, go ahead and open up a new document, new calculator page, and we're going to just go ahead and evaluate the log of 15. So to do that, you can type out log, open up a parenthesis, and then hit 15. If we hit enter, we can see that our calculator is going to assume that this is log base 10. If you're looking for a specific logarithmic base, you can hit control and then this 10 to the x. That's going to open up your log, where there you can type in your logarithmic base. You can also just skip over that box, and then your calculator is going to assume that it's a common log. So log of 15, if I hit control and enter, that's going to give me a decimal approximation of 1.176. Okay, so let's go ahead and fill in that answer. It's about 1.176. Now I want to evaluate log of 5 times log of 3. So back to our calculator, we have log of 5, and we're going to put that in parentheses, and then times log of 3. Okay, control enter, and that's going to give us a decimal approximation of 0.333. And then finally, if we have log of 5 plus log of 3, let's go back to our calculator. So we have log of 5 plus log of 3. Control enter. That's going to give us our 1.176. Okay. I notice that log of 15 and log of 5 plus log of 3 are equal to the same thing. Now let's try another. Log of 30 divided by log of 2. So back to our calculator. I'm going to do control divide to open up a fraction bar. So log of 30 divided by log of 2. Control enter. That's going to be 4.907. And then log of 30 minus log of 2. Control enter. That's going to give us our 1.176. Log of 8. Control enter. 0.903. Log of 2 and then cubed. So first we're going to open up a parenthesis and type out log of 2. And then we're going to cube that. So we're going to raise that to the third power. Control enter. And that is 0.027. And then we have log of 2 plus log of 2 plus log of 2. So log of 2 plus log of 2 plus log of 2. Control enter. We get 0.903. All right. And then finally, our last one, 3 times the log of 2. Control enter, 0.903. Okay. So let's see if we recognize any patterns. Let's start with this first group here. I notice that log of 15 and log of 5 plus log of 3 are the same. So maybe we can come up with a rule there. I also notice that that's also equal to log of 30 minus log of 2. Okay. Another thing that I notice is that we have log of 8 is equal to log of 2 plus log of 2 plus log of 2. And that's also equal to 3 times the log of 2, which kind of makes sense. Notice that it's not equal to the log of 2 cubed. And likewise, the log of 30 divided by log of 2 is not equal to the log of 15. So we can't divide those arguments of the log. Let's see if we can generalize a rule for logarithms. We'll start by reviewing for exponentiation. Remember our product rule for exponentiation states that if we have two exponents that we're multiplying that have the same base, what we can do with those powers is we can add those powers. Similarly, for the quotient rule for exponentiation, if we have two exponents and we're dividing, they have the same base, that's equal to that same base, but then we subtract the powers there. And then finally, the power rule, or power to a power, this would be if we have x to the a raised to the power b, we simply multiply those two powers. Okay? So for logarithms, we follow some similar rules. The product rule, where we have the same base and we add the exponents, it's similar for logs, where if we have log of a times b, this is equal to log of a plus log of b. Similarly, for the quotient rule, if we have log of a divided by b, or the quotient or ratio of a and b, this is equal to log of a minus log of b. And finally, the power rule, if I have log of a to the power of b, this is equal to b times the log of a. All right? Now notice that we wrote all of these rules using the common log, but know that this is true for all logarithmic bases. We could say log base 2 of ab equals log base 2 of a plus log base 2 of b. That logarithmic base is not going to change for any of these rules. Okay, so notice that it keeps that same logarithmic base. It's just how we compare these two quantities. All right, so let's get some practice. For number 1 here, we have log of 12. Given that a is equal to log of 3, b is equal to log of 4, and c is equal to log of 5, see if we can write these expressions in terms of a, b, and c. All right, so looking at this, I can see that 12 is a product of 3 and 4. So I could rewrite this as log of 3 times 4. Well, I know that using our product rule, this is equal to log of 3 plus log of 4. Okay, so splitting up that product into the sum of two logs. And then finally, we know what log of 3 is, that's a, and we know what log of 4 is, that's b. So this simplifies to a plus b. For log of 16, well, I know that this is equal to log of 16 is 4 squared. Okay, you could also write 4 times 4 and split it up into a product rule. I'm going to use our power rule here. I know using our power rule, this is equal to 2 log of 4, which is equal to 2 b. Okay. Number 3, we have our quotient of 3 and 5. So this tells me that this is equal to log of 3 minus log of 5. And this is equal to a minus c. Log of 75. This is log of 75 is 5 squared and then times 3. Okay. Well, I know that we can split that up. So we have log of 5 squared plus log of 3. And I know using our power rule that this is 2 log 5 plus log 3. And then finally, using that substitution, 2c plus a. All right, log of 50, this is equal to log of, this would be 2 times 5 squared, or this would be log of 2 plus log of 5 squared, which is equal to log of 2 plus 2 log 5. All right, so here we can substitute one of those logs for c. However, 2, we can write that as the square root of 4. All right, so this would be equal to log of the square root of 4. Okay, so we're trying to get this looking more like b. So in order to get this to look like b, I know that the square root of a number is the same as raising to the 1/2 power. So this tells me that we have log of 4 to the 1/2 plus 2 log 5. And finally, we have that power rule, 1/2 log of 4 plus 2 log of 5, which is equal to 1/2 b plus 2c. All right. And last one, log of 0.8. I know that 0.8, its fraction equivalent is 4/5. So that tells me log of 4 minus log of 5, or b minus c. All right. Let's go ahead and flip the page. So again, recalling these exponentiation rules, x squared times x cubed is x to the 2 plus 3, or x to the 5th. Similarly, for our quotient rule, x to the 6 divided by x squared is x to the 6 minus 2, or x to the 4th. Okay, we get these same rules here. Here's our product rule for logs. An example using log base b of 15 plus log base b of r is equal to log base b of 15r. We have our quotient rule. When we subtract two logs of the same base, we divide those arguments. Okay, and finally, if we have a coefficient in front of the log, we can put that inside the log and write that as a power of the argument. Okay, and vice versa for any of these. All right, so part 2, let's rewrite these as a single logarithm. We're going to condense these into a single log. Okay. All right, so here we have log base 5 of 4 plus log base 5 of 3. I can condense this into a single log using our product rule. And so this is equal to log base 5 of 12. Number 2, I notice that we'll start with this right here, and then we'll subtract that at the end. So we have log base 2 of 4 times 2, and then minus log base 2 of 8. Okay. Well, this is equal to log base 2 of 8, and then minus log base 2 of 8 would mean that we divide those arguments. So this is equal to log base 2 of 1. And so what we have here is anything, log base anything of 1 is equal to 0. Okay, so this evaluates to just 0. Number 3, 2 log of a minus 3 log of b. We can write this as log of a squared. That's our power rule. Minus log of b cubed. And then finally, we have a quotient. So this is log of a squared divided by b cubed. All right. Next up, we have log of x to the 1/3, our power rule again, plus log of x to the 2/3. All right. Now we have our product rule. So what do we do with those powers? We add them. So this is equal to, well, actually, let's go ahead and write out that step. X to the 1/3 times x to the 2/3. And again, we have those exponents with the same base. We can add those powers. This is equal to log of x to the 3/3, or x to the 1, or just simply log of x. All right. Number 5. We have 5 log x, so this would be rewritten as log of x to the 5th. We have plus log of y to the 1/2, and then minus log of z to the 4th. All right. So this first grouping, we have a power rule. So we have log of x to the 5th, y to the 1/2. And then we have minus log of z to the 4th. Now we have our quotient rule, log of x to the 5th, y to the 1/2, all over z to the 4th. Okay, and that's our answer. Number 6, I'm going to first start by distributing this into the grouping here. So we have 1/3 log base 2 of b minus 1/3 log base 2 of c. Now we have our power rule, log base 2 of b to the 1/3 minus log base 2 of c to the 1/3. So now we have a quotient rule. We have log base 2 of b to the 1/3 over c to the 1/3. Now, if I were to rewrite this using radicals, we would write this as log base 2 of the cube root of b over the cube root of c. We can't have a radical in the denominator here. So in order to get rid of this radical in the denominator here, the cube root of c, we have to multiply it by the cube root of c 3 times to get rid of that cube root. So essentially we're looking to cube the cube root of c. So in order to cube the cube root of c, we need to multiply it by 2 more of the cube root of c. So this is equal to log base 2 of cube root of bc squared over c. And this is our final answer. Okay. All right. Number 7. Here we have x log base 4 of m. This will be rewritten as log base 4 of m to the x plus we have log base 4 of n to the 1 over y, and then minus log base 4 of p. All right. Product rule, log base 4 of m to the x times n to the 1 over y, and then our quotient rule all over p. Okay. Number 8, there's a few ways you could do this one. I'm going to start by distributing this negative 4. So log base 5 of y, and then minus 4 log base 5 of q, and then minus 8 log base 5 of x. All right, so we're distributing that negative 4. Okay, so now we'll start with this first grouping here. So we have log base, actually before we do that, let's deal with those coefficients. So we have log base 5 of y, and then minus log base 5 of q to the 4th, minus log base 5 of x to the 8th. Okay, so now let's go ahead and group these first two terms. So we have log base 5 of y over q to the 4th. Okay, and that's minus log base 5 of x to the 8th. All right, so now we're going to divide this again. Now remember, dividing by a fraction is the same as multiplying by the reciprocal, right? So this is equal to y over q to the 4th times the reciprocal of x to the 8th, or 1 over x to the 8th. So this is equal to log base 5 of y over, let's write that, q to the 4th, x to the 8th. There we go. All right, that's our answer. Let's go ahead and flip the page. Now we're going to expand the logarithms. We're given a single log, and we're going to expand it into an expression, a big long string of logs. All right, so here we have log of x, y, z to the 4th. This is a bunch of products, and then we've got a power in there. So this is log of x plus log of y plus log of z to the 4th. So we have log of x plus log of y plus 4 log of z. All right, and that's our answer. Number 10, we have a couple products and a quotient. So let's start with the quotient. This is equal to log of 5x minus log of 4y. Now we've got these products, so log of 5 plus log of x, and that whole thing is subtracting log of 4 and then plus log of y. These parentheses are important here. Because we want to subtract that whole denominator, this whole grouping here, we have to include those parentheses. All right. Number 11, I notice that this whole thing is square rooted, so we could say that's the same as raising to the 1/2 power. So this is log of 2r over 5w, and that's to the 1/2 power. Okay, so this is equal to 1/2 times the quantity. We've got, let's do that quotient, we'll split that up. So log of 2r minus log of 5w, and just like before, we have to use those parentheses. So 1/2 log of 2 plus log of r, and then this is minus log of 5 plus log of w, and then we're multiplying that whole thing by 1/2, so that whole thing has to be grouped as well. Okay. Number 12, here we have the numerator is raised to the 1/2 power, and then we've got a few things in the denominator. So this is equal to log base 4 of, let's start with the quotient. So we'll say x plus 9 to the 1/2, and then we're subtracting log base 4 of s squared t to the 1/3. All right. Now we'll bring out that power. So we have 1/2 log base 4 of x plus 9. And then we have a product here. So I'm going to say log base 4 of s squared, and then plus log base 4 of t to the 1/3. Okay. And that needs to be a grouping there with parentheses because we're subtracting that whole quantity there. Okay. Finally, let's deal with those powers. We'll bring that out front, and then that'll give us our answer. So 1/2 log base 4 of x plus 9. That cannot be simplified or expanded. By the way, we've got separation by addition inside that argument, so we can't do anything there. Minus parenthesis 2 log 4 of s plus 1/3 log base 4 of t. All right. All right, number 13. Two students are working on the same problem. Which one simplified it correctly? So we'll start with, we're looking at log base 3 of x to the 4th divided by 7. Student A wrote this first as a quotient, it looks like. So log base 3 of x to the 4th minus log base 3 of 7. Okay. And then the student pulled out that 4 out in front using the power rule. Okay. Student B recognized the quotient here, but then pulled out that power to the coefficient of the argument here. All right, so which one of these simplified this correctly? I'll let you take a moment, think about it. The correct answer is student A. Student A's is correct. All right, the reason why is with the power rule, that power comes out to the front of the log. It's the coefficient for the log, not the argument of the log. Let's check out our last one for today. Two students are working on the same problem. Which one simplified it correctly? We're condensing now. I noticed that we have, looks like a product rule and then also the quotient. So here we have the student wrote this as a product of 8 and 2, or 16, and then minus log base 2 of 4. And then the student wrote this as a quotient, 16 divided by 4, gave us log base 2 of 4, which, by the way, can also be evaluated. Student B wrote this as, let's see, the student wrote this as the sum of 8 and 2, which is 10, and then also the difference of 10 and 4, which is 6. So again, I'll let you take a moment, think about it. What's your answer? The correct process here, the correct solution is student A again. Remember, this is a product and quotient rule. So we need to multiply the arguments together. Okay. All right. And by the way, this evaluates to 2. In case you wanted to take it one step further, I always say if you can evaluate, go ahead and evaluate. Tell me what that numerical value is. Okay. Okay, one last thing that I want to talk about today is the proofs or other properties of logarithms. I want to start with this problem. How would we evaluate the log of base 7 of 9? Okay, this one might be tricky because remember, we're asking ourselves to what power would we raise 7 to get to 9? This is not a whole number. In order to evaluate this with most calculators, you can use the change of base property. And what that is if you have log base a of b, we can rewrite that as log base c of b divided by log base c of a. Or in other words, what we can do is introduce a new logarithmic base, c, and that can be anything. It can be the common log, it can be the natural log, it can be any number. And then we take the ratio of those logs of the arguments b and a, okay? So this here, suppose I wanted to write this using the common log, okay? Most calculators that have logs definitely have the common log. Not all can do other logarithmic bases. So we'll say for simplicity's sake, we're just going to say the common log. So this would be equal to the log of 9 over the log of 7. And if I wanted to evaluate that, I could plug that into my calculator. Control divide, log of 9 divided by log of 7. Control enter. That's going to give me about 1.129. Okay. So now let's go ahead and use our change of base formula to evaluate each of these logs and rounding to the nearest hundredth. Okay, so log base 4 of 92, I could write this as log of 92 over log of 4. And this is equal to control divide or control enter, and we get 3.261. 261. 3.262. All right. Next up, log of 18 over log of 6. All right. So control divide, log of 18 divided by log of 6, control enter, 1.613. All right. One more property for today. If we had 3 to the power log base 3 of 7, I want to know what that's equal to. Now remember, if we were just looking at this exponent here, this would be saying, to what power would I raise 3 to get to 7? Okay, so if I were to rewrite this, say call this x, this would be rewritten as, well, if I were to say log base 3 of 7 is equal to x, this would be 3 to the x is equal to 7, right? Well, I know that this whole quantity here is 3 to the x, right? If we're calling this is equal to x, this is equal to 3 to the x. So I know that this is equal to 7. Or in other words, if you have b to the power log base b of x, if you're raising an exponent of a log to that same base, that exponential base is the same as a logarithmic base, it's just simply equal to the argument of the log there. And the reason why that is because think of this as a composition of functions, an exponential and a log composed together. A log is inside the exponential function. Because these two functions are inverses, the operators cancel out, and we're just left with the argument x. Okay? So for something like number 3, where x is equal to 2 to the 2 log base 2 of 4, well, this exponent here, I see that we have our power rule. So this is equal to log base 2 of 4 squared, or 16. So because we have that same thing, that exponential base is the same as the logarithmic base and the exponent, it's just equal to the argument, or 4 squared. Okay, so x is equal to 16. For number 4 here, we don't have that same base. We've got base 3 in for the exponential and base 9 in the log. Okay, so one way I can write this is I want to get the same base. So I want base 3 or base 9. Well, looking at this, I want to cancel out that log, so I'm going to look for base 9. So how can I rewrite 3 as an exponent of base 9? Well, I know that 3 is equal to 9 to the 1/2 power. So this is equal to 9 to the 1/2, right? And then we're raising that to the log base 9 of 100. Now we're raising a power to a power, so this is equal to 9 to the 1/2 log base 9 of 100. And then finally, using that power rule, we have 9 to the log base 9 of 100 to the 1/2, or the square root of 100. And so we find that x is equal to 10 here. Okay. So these have been our notes on properties of logs. We saw expanding, condensing, and then a few other properties, change of base, and then composing exponentials in logs. All right, we're going to get a lot of practice in class, so we'll see you tomorrow. Goodbye, everyone.